Hello everyone. So in the last class we had already discussed about SN1 and SN2 mechanism. Today we'll be learning a third type of substitution reaction which is called as substitution nucleophilic neighboring group participation. So when we talk about neighboring group participation, we need one leaving group in the molecule as well as one other molecule or another nucleophilic center in our carbon chain. Let's see how this reaction takes place. I'll be explaining you the whole mechanism using one example. Now let's say I have taken CH2X, CH2 and the other leaving group. Okay. So now when I'm talking about this molecule, first of all just note that this X and Lg are on the anti-position with respect to each other. And this is one of the mandatory condition also for NGP reaction to happen. Whenever we are talking about this setup, there is a sigma bonding orbital over here. And in the opposite plane, we will have sigma anti-bonding orbital. Now what will happen? Because of this leaving group presence, this carbon will get a partial positive charge and this leaving group will get a partial negative charge. Because of this partial positive charge, this X will get attracted toward this carbon and will try to form a bond, but will form a bond using this sigma anti-bonding orbital. So when it will try to make a bond with sigma anti-bonding orbital, more the bond formation, the process will go towards the bond formation. This existing bond will become weaker, weaker and weaker, and eventually the bond between carbon and leaving group will break. Hence, the formation of a non-classical carbocation will take place. We have already discussed what is non-classical carbocation in GOC. So a structure like this will be formed. So this is how the compound, this is how an intermediate state will be formed. This is called as non-classical carbocation. Because there is a formation of non-classical carbocation is happening, this reaction rate is very fast. This reaction rate is nearly 1000 times faster than SN1 and SN2. So this is nearly 1000 times faster than SN1 and SN2. When you read some good level of books, there you will find in many of the books they would have compared directly the compounds doing SN1, SN2 and SN-NGP, and the rate of SN-NGP is much faster than SN1 and SN2. So they have given the exact values of the rate differences between NGP, SN1 and SN2. So this is our non-classical carbocation. Till now, the nucleophile attack has not happened. So all of this has happened even before a external nucleophile attack will happen. So here, let's say now the nucleophile comes into the picture. And for nucleophile, there are two sides to attack. One is it can attack on this carbon. Another, it can attack on this carbon. It can either break this carbon and X bond, or it can break this carbon or this X bond. Because this molecule is symmetric, it won't matter on which carbon this nucleophile is attacking, and hence we'll get one straight single product. In other cases where the chain is not symmetric, you will get different products formed depending upon in which carbon it is attacking. So basically, two different carbons we will have as a site to attack, and we will get two different products formed. Here we will get CH2X, CH2 nucleophile. This will be the product formed. Now again, look at it very carefully. Look at the configuration of this carbon where the nucleophile is present, and just check the configuration of the initial molecule where the leaving group was present. That carbon's configuration and this carbon's configuration is exactly same. So what we can, what information we can derive from this? That retention of configuration takes place when this NGP reaction takes place. And why is it so? To understand that, just again go back to the non-classical carbocation and try to understand. So this was the position of leaving group, and when X attacked on the anti-bonding orbital, at that time, and formed this non-classical carbocation. This was in the opposite direction as compared to LG, or the leaving group. This side is the opposite side from the opposite side with respect to the leaving group what we had earlier. So when nucleophile will come to attack, this place is already crowded and it will face a repulsion from this X. Hence will not attack from this end, instead will attack from the bottom, either on this carbon or this carbon. When it will do attack on this carbon or this carbon from the bottom side, this was the position of earlier leaving group also, and hence the retention of configuration will take place. Again I'll explain you. So the classical carbocation has formed in the opposite direction with respect to the leaving group. And once the non-classical carbocation has formed, when the nucleophile will attack, it will not attack from the side where already X is present, because it will face a repulsion over there. Hence it will go to the opposite side and will attack on the carbons, the possible carbons, and hence will retain the configuration. So what are two important points of this reaction? First is, for this reaction to happen, are two groups which will participate in substitution reaction. Those should be in the anti position with respect to each other. And second important point is, once the product is formed, retention of configuration will take place. In SN1, what we have learned, in SN we have learned that racemization will happen once the reaction will take place. We will have retention products also, and we will have inversion products also. When we talk about SN2, complete inversion takes place, whereas in SN-NGP we will have complete retention of configuration. Okay. I hope you have understood what we have done just now. Next we'll be talking about types of SN-NGP reactions. So what all different reactions we have for SN-NGP, or what all different groups can do SN-NGP. First is NGP by. First is NGP by unshared pair of electrons. So basically these are nothing else but lone pair. Next is NGP by pi electrons. Third is NGP by aromatic rings. Fourth, NGP by cyclopropyl group. And the fifth one is NGP by sigma electrons or sigma bond. Okay, this cyclopropyl group, we can also call it as cyclopropyl ring. Sigma electrons are also called as sigma bonds. Okay, so let me summarize. We will do all these types in detail. Let me summarize about NGP. So what is happening in NGP? We have two different groups attached on the neighboring carbon. One is the leaving group itself, and one group which has the lone pairs available. So that the species which has lone pairs, the lone paired species, will give its pair of electron to carbon, the partial positively charged carbon which is attached to the leaving group, and will kick out the leaving group, will form a non-classical carbocation. And that formation of the carbocation will be in opposite direction with respect to the leaving group. Incoming nucleophile will attack exactly in the same direction where the leaving group was. It will have two possible options of attacking on the carbons. One, because it is capable of attacking on this carbon as well as on this carbon. So both the neighboring carbons can get attacked by the nucleophile rather than only one. And wherever the attack will happen, it will attain the same configuration as the original configuration. So the nucleophile will come exactly in the same position where the leaving group was present. In the same configuration it will attach. For neighboring group participation to happen, we need both the groups in the anti-position with respect to each other. Why anti-position? Just understand this. If it is not in the anti-position, let's say I take a case where I have CH2X and CH2 leaving group in the same position, not in the anti-position but in the syn position, these two will repel each other. So repulsion will happen, and this X will not be able to approach this carbon to form the carbocation, or it will not be able to get attracted towards partial positively charged carbon to form a new bond. So this reaction will not proceed. So hence we require exactly anti-position for this reaction to happen. We have 5 different kind of NGPs which can happen. One is by lone pairs, one is by sigma bonds, one is by pi bonds, one is by aromatic rings, and one is by cyclopropyl ring. Okay. Next, let's see how NGP. We have already discussed this NGP by unshared pair of electrons. We will see all these cases in further more detail now. So now we have understood how NGP works, how the mechanism works, and now we'll do some questions to get a better understanding of the concept. So let's take first example. Assume I have CH3, CH2, S, CH2, CH2, Cl. Okay. Now, even this sulfur is the one, sulfur has the lone pairs present on it which can attack on the carbon where the chlorine is present. Now this sulfur will try to form a bond on the anti-bonding orbital of this carbon and will try to break the bond between carbon and chlorine. Eventually this will get converted, and this step will take place even before a nucleophile will attack. So what will happen? CH3, CH2, S, CH2, CH2. This sulfur will start forming a bond with this carbon, and the bond between carbon and chlorine will start breaking off. And this molecule will look like this: CH3, CH2, S, CH2, CH2, and plus. So this is how the carbocation, not carbocation, sorry, this is how the positively charged cation will be formed, and this will be a non-classical cation setup. Okay, so now after this, once the sulfur has got a positive charge, now nucleophile will come into the picture. So all these steps have already performed or already have taken place even before your nucleophile could have attacked on the molecule. So initially I have not mentioned, so now I am mentioning that we had a nucleophile as MEO minus, but even though we had an MEO minus, it has not come into the play yet. Now this MEO minus can attack on both the carbons. It can attack on this carbon and it can attack on this carbon also. So let's do one thing to just distinguish the path of the reaction and just to understand what will happen if it will attack on this carbon, if it will attack on the other carbon. I'll do one thing. I'll just mark one carbon as a carbon 14. So let's say the star marked carbon is carbon 14. Okay. So this is my carbon 14. This is again my carbon 14. So now we have two options. One is carbon 12, one is carbon 14. Now MEO minus can attack on this carbon 14 also. And this MEO minus can attack on the, or nucleophile can attack on this carbon also. So let's see what all different products will be formed. If I go by path A, assume attacking on carbon 14 is called path A. The product form would be CH3, CH2, S, CH2, CH2, OMe, right? And this is my carbon 14. I can also write it as CH3, CH2, S, CH2, CH2, OMe. This is how I can write. And just notice the positioning of OMe is exactly at the same position where the chlorine was. And by the way, as I have already mentioned before, that the retention of configuration will also take place. So it's not only the position is same, but the configuration of the carbon will also remain same. Now let's see what will happen if the reaction will happen through path B. So this is the product through path A. And let's see what will be the product from it if we'll have path B. So let's say if reaction takes place through path B, the products formed would be, so basically the nucleophile attack will happen on this carbon. Nucleophile attack will happen on this carbon, and the bond between this carbon and sulfur will break. Hence, we'll get the product as CH3, CH2, S, CH2, CH2, OMe, and now this sulfur is attached to carbon 14 directly, and the positioning of carbon 14 is here. So these are the two possible products what I will get if the neighboring group participation will happen. Now what we can observe over here is that if you notice in this path, product formed by path A and product formed by path B, we have seen the shift or change in the position of carbon 14, which was not possible in this SN1 reaction or SN2 reaction or whatever substitution we have learned till now. So this kind of change in positioning of the atoms is only possible in the NGP reaction. Okay, so this is one example. Let's go to the another example. Let's see the another example. Okay, before going to the another example, I'll just quickly go through the whole thing. So this is the molecule what I have taken. I have sulfur and I have chlorine and I have the nucleophile in the solution as MEO minus. Now even before MEO minus can attack on chlorine, the sulfur internally will attack onto the carbon in the anti-bonding orbital, will try to form bond over there. So in that process of forming the bond between carbon and chlorine will go weaken, and the new bond between sulfur and carbon will form, eventually forming this kind of cation. Okay, now a nucleophile will come into the picture and will start attacking on the carbons. Now when it will attack on the carbon to replace this sulfur or replace this nucleophilic end, this can attack on this carbon, which is carbon 14, and it can also attack on the normal carbon. If it will attack on the carbon 14, the chain will break in, chain will form in such a way that the bond between carbon and sulfur will break, and sulfur will be attached to normal carbon 12, then carbon 14, and then OMe will be attached to it, and this will be the product formed. Whereas if MEO will attack on carbon B, if MEO will attack on carbon 12 by pathway B, in that case the bond between carbon and sulfur will break, and we will have CH3, CH2S, CH2, CH2, OMe. So this will be the product formed, and we can see the shift in the position of carbon 14. This is possible only in NGP. Again, I'm again repeating, in NGP the retention of the configuration will take place, and NGP is only possible when these molecules are, when the lone pair species and the leaving group both are in the anti-position to each other. If they are not in the anti-position, the reaction will not take place through NGP. It may happen through normal SN2 or may not happen at all depending upon the situation, but will not happen through NGP. Okay, now let's see the another question. Now let's see the another example. This is example 2. Now let's say I have taken a molecule like so this is my molecule. Now what will happen, just look at this molecule again. What is the lone pair species over here? Both oxygens are lone pair species though, but OTS is definitely a better leaving group. So this will be acting as a leaving group. Okay, and this oxygen will give its pair of electron to this carbon to form a bond. So this pair of electron from oxygen, so my oxygen will try to give its pair of electron to this carbon to form a new bond and will try to kick out this OTS, which is anyways a good leaving group. So we will have a cation formation like this. So my molecule will look like this. This is how my molecule will look like after removing of OTS, after the removal of OTS. As we had the nucleophile in the solution, but it has not started attacking on it yet. After this whole rearrangement will happen, now CH3OH will attack. Now the CH3OH can attack on this carbon also and can attack on this carbon also. Or let's take a better nucleophile. Instead of taking CH3OH, I can take it as CH3O minus itself to make the reaction rate better. Let's say I have taken CH3O minus and CH3O minus. So now again there are two, in the previous situation what was the condition? In the previous situation we had the symmetric carbons unless I made it C14 and C12. The ends were symmetric and hence we would not be able to see the difference in the product formed. After making carbon 12 and carbon 14 we could actually see some change in the reaction. Now here I have taken a totally non-symmetric molecule. So what is happening here? Now this CH3O minus can attack on this carbon, that is path A. And it can also attack on this carbon. This is called path A. Now, which path nucleophile will choose to attack on? Now in this, my CH3O minus is acting as a nucleophile. The CH3O minus can attack on this carbon and can also attack on this carbon. Okay, and this will attack from the opposite plane as compared to what OCH3 is attached to. So this mechanism is very similar to SN2 mechanism, and in that case it will look out for the steric hindrance factors also. Wherever the steric hindrance is more, reaching out this nucleophile to the carbon will become very difficult. So rather than opting for pathway B, this nucleophile would like to go by path A, so that it can face less steric hindrance and can break the existing bond and can make a new bond. So it will not go through pathway B, but it will follow path A, eventually forming the molecule as, so this CH3O will attack on this carbon, will break the bond between oxygen and carbon, and the chain will look like this. And the chain will look like this. OCH3, retention of configuration, and here this will become like this. So my OTS has got replaced by OCH3, my OTS has got replaced by OCH3, and retention of configuration has taken place. Internally, the attack of one electron-rich species or the species which can give a lone pair has attacked on OTS, had made a carbocation, a cyclic carbocation. Then later the nucleophile has attacked on the best carbon possible, where the less steric hindrance is, and this molecule has formed. Now this way it has done NGP with some sort of SN2 also. So NGP sometimes is also called as internal SN2. Do not get confused with internal SN2 or intramolecular SN2. Intramolecular SN2 is very similar to NGP. So NGP can be, your intramolecular SN2 can be extended to NGP also. We will see those examples also later on. Now we'll see an example where pi electrons will be participating in NGP. We'll be taking an aromatic ring also, which will do NGP. So while doing NGP reaction, if you are taking an aromatic ring, just make sure that after the product formed, your aromaticity should be maintained. If you are forming a compound where the aromatic compound is converting into a non-aromatic compound, in that case the reaction will not take place the way we are assuming, or the product form will be unstable product. Okay, so you have to make sure you will do NGP on an aromatic ring only and only if you can maintain the aromaticity once the product is formed. Now let's take the example. This is our benzene ring, and we have CH2, CH2, Cl attached to it. Now these pi electrons, and we have water as a nucleophile. Now these pi electrons will try to attack on this carbon where this leaving group is present. Will try to attack on this carbon to form a bond, and will break the bond in such a way that a positive charge will form over here, and a new bond will form between this carbon and this carbon. So how will it look like? Let's see. What will happen? The bond between this carbon and this carbon will form. Bond between this carbon, the pi bond between this carbon and this carbon will break, and a positive charge will be formed here. Chlorine will go out. So your carbocation will look like this. A positive charge over here, CH2, CH2. New bond formed between this carbon, and chlorine is out, and other bonds are exactly in the position where they were. So this is the carbocation formed. Now when the water will attack, oxygen of water has two positions, possible positions where it can attack. One is on this carbon and another is on this carbon. Because the system is symmetric over here, so it won't matter where our oxygen is attacking. Let's assume it is attacking on this carbon. Then the product will look like this. CH2, CH2, OH2 plus, and a pi bond will restore over here. How this pi bond got restored? This CH2 had broken the existing bond between this carbon, giving back the pair of electron to the carbon, and due to the electrons which we have given to this carbon, a bond formation will happen again between this carbon of the ring and this carbon of the ring. This CH2 will form the bond with H2O. Now O will get a positive charge over it. Because of this positive charge, oxygen will try to get rid of it by breaking the bond between oxygen and hydrogen, and we will get CH2, CH2 and OH. So we have got a protonated alcohol here. It will lose one hydrogen, and we will get this as a molecule. Here again the retention of the configuration will take place. Let's summarize this again. We had a benzene chain over here with CH2, CH2, Cl. Now the pi bond here between one carbon of the benzene chain and other carbon will break in such a way that pi electrons will try to form a bond with the alpha carbon. The positive charge will be gained by the adjacent carbon, which has shared the adjacent carbon, which is forming bond to the alpha carbon. Now after this, we will get a three-membered ring over here, CH2, 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 and a positive charge on the so-called benzene ring, which is no more benzene. The aromaticity of this ring has been broken now. Now this H2O can attack on this carbon as well as on this carbon. Here it will not matter in which carbon it is attacking. So let's assume that it is attacking on this carbon. This carbon will break the bond with the carbon of benzene, and the electron pair will go back to that carbon, forming the pi bond again with this positively charged carbon on the benzene ring. And this CH2 will form a bond with H2O, forming a protonated alcohol. This protonated alcohol will lose a hydrogen to form a normal alcohol. So this is the reaction where we have seen This is the reaction where we have seen pi electrons participating in NGP as well as the aromatic ring participating in the NGP. In such cases, you have to be a little careful so that you do not lose aromaticity of a molecule while doing the reaction. In the product, the aromaticity should be retained. This is a very important example. Try to solve many questions, try to solve more examples of such kind so that you can have a better hold on this concept. So this is the question on the same concept what we have learned just now. So we have seen multiple examples of it. Try this on your own and I'll discuss the solution. So let's see the explanation of this question. This nitrogen is the lone pair species which will attack on this carbon 2 where bromine is attached and will try to form a bond over here by breaking the bond between carbon and bromine. So we will get the product formed as nitrogen CH3. It would form a cyclic ring cation. This is carbon 1, this is carbon 2, CH3 and a plus charge over it. So this is how the structure of a cation will be formed. Now after this, my KOH will attack on it. Now KOH has two possible options. One is either it can attack on carbon 2 or it can attack on carbon 1. Where it would prefer attacking? It would prefer attacking on carbon 1. Why? Why? Less steric hindrance. So when it will attack on carbon 1, the bond between nitrogen and carbon will break and the OH will attack on carbon 1. So how the new structure will look like? It will look like this. Nitrogen, CH3, 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 this is carbon 2. Carbon 2 is still connected to carbon 1 and carbon 1 is connected to OH. So this is how the structure will look like. Now what we can notice over here is there are few things which we'll notice. First of all, position of leaving group and position of nucleophile with respect to the carbon is different. So position of leaving group was on carbon 2, but the position of incoming nucleophile is on carbon 1. So position of nucleophile and leaving group can be different. Second, irrespective of whichever carbon your nucleophile is attacking on, the retention of configuration will still remain. The configuration will still remain the same. So retention of configuration will take place. So if let's say carbon containing leaving group was R, then carbon containing nucleophile will also be R. So retention of config will take place. And these kind of changes in terms of positioning of nucleophile and leaving group or switching off the whole carbon itself from here to there, you will see mostly in the NGP. Okay, until unless the reaction is going through carbocation formation and carbocation rearrangement is happening. There also you may see that the leaving group is on a different carbon and the incoming nucleophile is going to the different carbon. And the second such case is the NGP. Okay, so these are the examples of NGP. Try to do as many questions of NGP as possible so that you can get a better hold of it. Many questions in advanced paper have been asked from this area. So this basically the questions of NGP includes. There will be questions where you will have lot of concepts included in a question, including NGP also. So you should know how to identify whether NGP is happening in a reaction or not.